So I wanted to do some examples together with you guys dealing with weak acids and bases. And so we're just going to run through a couple here. Um, and just as always, kind of think about the thought process that goes into how we approach the problem as well, recognition steps. So we see that we have a problem here that's what's the pH of a 5.0 molar HF aqueous solution, and then they're given a Ka. So a couple things here, all right, we're after pH, so we know that eventually what we need to calculate is we're going to need to calculate H3O plus concentration at equilibrium. So that's going to be our ultimate goal because then we know we can do the P operation and take the negative log of that information. We're given an acid to start with. How do I know this is an acid? Two different reasons, okay? I see that it has an H that's listed in the front and it's aqueous. Just like last semester when we identified acids that way, it applies here as well. I also see that I'm given a Ka. So Kas are associated with acids, all right? So I know that I'm going to calculate H3O plus at equilibrium. I know I have an acid because of the Ka and seeing that H with something attached to it being aqueous. The other thing that we know is we see we have a Ka, so we know we have a weak acid. Now, how do we know that? We sort of mentioned this briefly before. I'm going to just say it again because it's really important. We know that when we have weak species, you have an equilibrium constant because equilibrium constants imply that the reaction does not go fully to the right, okay? So whenever we're given Ks, we know it's weak. We know we're going to be doing ice table type problems. So with all those recognition steps done, let's go and let's set up our calculation, right? So here's the thing, different from last chapter. I identified HF as a weak acid. I'm not given the reaction to start with, but I do know how to react acids with water to make the appropriate species to use a Ka. So for every Ka problem, I now come up with the chemistry where I take my acid, I react it with water, and what I get is hydronium, right? And the conjugate base. And remember, think about the H moving to the H2O, so the conjugate base is going to be F minus. It's a weak species with a K. So I'm going to do an ice table. What do I do with liquids inside ice tables? With liquids inside ice tables, we X them out. What initial information are we given about H3O plus and F minus? We're not given any. Now you might be saying to yourself, wait a second, we just went over water as having an H3O plus concentration to start with of 1.0 times 10 to the minus 7th. Before I dump the HF in there, isn't that in there to start with? And the answer is yes. It's just that this is so small that in problems like this, what we do is we say, this is so small compared to what we're going to get that we're going to pretend it's zero because that'll simplify our analysis, okay? So realize that there is a little bit of that in there, right? But it's so small that we're just going to call it zero for this sort of problem. Our initial concentration of HF is 5.0 molar. We do a Q versus K. Q equals 0, so Q is definitely less than K. So we know which way the reaction is going to progress. We know it's going to progress to the product side. So now I'm going to put in minus X here. I plus C equals E. I'm going to put a plus X here and here. I plus C equals E. I plus C equals E. So now I'm ready to attack this problem from a mathematical standpoint. I know that my K expression is going to look like my H3O plus concentration, my F minus concentration, all over my HF concentration. And why is water not included? We reminded ourselves that we're just going to go ahead and cross that out because it's not needed, all right? So now let's get into the math part. Remember, our goal is we're after a pH. We have our setup. We can take the information from our ice table and we can substitute it into this K expression. The K that I gave you previously was 7.2 times 10 to the minus 4, all right? From our ice table, each of these things on the top here in the numerator, this was an X, this was an X. Each of those is an X, so I'm going to have an X squared. In the bottom from my ice table, my HF was 5.00 minus X. right? That equilibrium information from our ice table. Remember, to populate K, you take equilibrium information, was 5.00 minus X. All right? K is small, so the reactant side are favored. I'm moving towards the product side. I'm moving in the unfavored direction, right? I see this as 10 to the minus 4. I see this as 10 to the 0. This is a great opportunity to use the 5% rule. All right, so all those 5% rule checks, those ideas come into play. We're moving in the unfavored direction. All right, remember this is a weak acid, so the reactant side is going to be favored, but we're moving to make products. Okay, so let's assume that X is way less than 5.00. Our math simplifies down. 7.2 times 10 to the minus 4 equals X squared divided by 5.00, right? We can then solve this for X. Make sure you can fill in this math that I'm doing here to solve for X. And the X that I get with the 5% rule is 0.060, okay? And like I said, be able to come up with that yourself. If you want to practice the quadratic formula, also practice it, you'll get something near here, right? We're going to do our 5% rule check. And I'm going to see, okay, this X, it does look pretty small relative to 5, but let's make sure mathematically it is. Let's take 5.00. We subtract our X minus 0.060. Divide it by the number that we took it from. Multiply by 100. And what I get is 98.8%, which is within 5% of 100%. So my 5% rule works. So that's a good answer. Look at your ice table, all right? On your ice table, X is the concentration of H3O+. What do we need? We need a pH. pH for this problem is the negative log, well, for any problem, is the negative log of H3O+. But for this problem, right, from our ice table, X was our concentration of H3O+. So the pH for this is the negative log of 0.60. We plug that into our calculator. We pay attention to significant figures. There's two total significant figures here. We're doing an LOG. What we get is 1.22, two total significant decimal places here. So our final answer for our pH is 1.22. Always make sense of your answer. Do we have an acidic solution? Did we decide it was an acid at the top? Yeah, right at the top we even wrote down the word acid, all right? Does this pH make sense for an acidic solution? And the answer is yes. The pH is less than 7, so this answer makes sense, 1.22. Right, that's the pH of that solution. So again, once we set this up, we invoke some rules that we learned in the last set of videos last week, but it's the same sort of math. Now the new stuff was being able to set up the chemistry and then go from there, right? Oh yeah, set up the chemistry, be able to fill out your ice table, and then maybe there's some steps at the end like calculating a pH. That's the new stuff. But again, if you can't write down the correct chemistry, then you're gonna have an issue even getting here, and then you're definitely not gonna be able to get here. So again, please make sure you can focus in on that chemistry. Let's do another example dealing with an acid, and then we'll do one last example in this video dealing with a base. So for 2, right, a solution with 1.00 molar HA has a pH that's equal to 5.241, right? What is Ka for this acid? All right, what is Ka for this acid? So a couple different things from a recognition standpoint. Again, I see HA, all right? You can assume that the solutions are aqueous. We're talking about a Ka, we definitely have a weak acid. So we know we're gonna be writing an ice table for this guy, right? We see that we're given a concentration and this of your acid to start with, right? A solution that's made like that to start with. Then we also have the pH, which gives us equilibrium information, all right? Let's start by setting up the ice table here, right? Again, why do I know I have to set up an ice table? I have a weak acid. It's referenced that it has a Ka, right? It's referenced that it has a Ka. So I know it's going to be in equilibrium. HA. What do I do with acids? React them with water to produce hydronium and the conjugate base. ICE, cross out H2O. We're given that this solution is 1.0 molar in HA. Again, we can assume that we have none of these to start with because we're given that there is none of that amount there. We're not given any information about it, so you can assume it's 0. All right. Which way are we going to go? Q is equal to 0, so Q is less than K. All right, whatever K is, it's not going to be less than 0. So we're going to move in this direction. So we're going to put a minus X here, plus X here, plus X, X down here, X down here, 1.00 minus X. So I'm after Ka, and I have a given pH. Wait a second. I know once I fill out an ice table, I can take this E information and I can equate it to Ka. I know that my Ka expression comes from this part of my ice table. So Ka, based off of this, is going to be that concentration and that concentration at equilibrium. X times X gives me X squared, over this concentration at equilibrium, 1.00 minus X. Okay? So it looks like I'm stuck at this point. Okay? What we have is a situation where we have one equation here, but two unknowns, Ka and X. And then here's where that last bit of information that we didn't use comes into play. Excuse me. What we have is a situation where X is actually known. Okay? Now, why do we know X? Because what we were given with our pH was that the pH was 5.241. We also know that pH is the negative log of the H3O plus concentration at equilibrium. Okay, well, the H3O plus concentration at equilibrium, if I look at my ice table, that's the same for this problem. Looking at my ice table, that's the same as X. So can everybody make that connection? If you have the pH, we know that the pH is the negative log of H3O plus at equilibrium. Well, I have that information right here, right? So I can replace that value with X. Oh, so X is actually going to be known when we go and do this Ka expression. So bring the negative to the other side. The log of X is minus 5.241. All right. Let's take the anti-log of both sides. Raise both sides as a power of 10. What we see here is this cancels out. And what we get is an X that's equal to 5.74116 times 10 to the minus 6. That's our X. Let's check significant figures. There's 3 significant decimal places here, so there would be 3 total significant figures here. This X then is the same X that's here, and it's the same X that's here. So what we can do is we can plug this back in, and please check my math. And what we're going to get is, all right, take our X and we square it, and then we divide by 1.00 minus X, which looks a lot like 1.00, okay, because our X is going to be small again. And what we get is 3.30 times 10 to the minus 11. Again, make sure you can fill in, all right, the intermediate steps. But again, this is a very important problem in terms of organization with an ice table. Knowing the pH really means that we know the H3O plus concentration at equilibrium. And if we know that, then we know the concentration of the conjugate base at equilibrium, and we know the concentration of our starting acid at equilibrium, and so we're able to calculate a Ka. All right. You'll see problems like this. You have seen problems like this. We did problems last chapter where we worked from equilibrium information to I information, and that's the same thing that we did just here. One last example. This really takes a lot of practice. You guys are doing well with the adaptation to the online course, and I appreciate the work, so just make sure you put in as much practice as necessary. All right, be able to identify the correct chemistry. So what is, last example, example number 3, what is the pH of a 1.0 molar NH3 aqueous solution given that Kb is equal to 1.85 times 10 to the minus 5. Okay. You could stop this and try it for yourself if you really feel ambitious, all right? I'm going to start to set it up with our analysis steps. We definitely don't have an acid here. I don't see that the species that's in front, I don't see that the species that's given to me has an H out in front. Ammonia is an example that we already went over. That's definitely a base. The other reason I know it's a base is because I see I'm given a Kb. So importantly, I know it's a weak base, because if we're given an equilibrium constant, then we know we're setting up an ice table because we have a weak species. All right. So what does this look like in terms of the reaction, in terms of the chemistry? NH3 aqueous, okay, all bases are the same. I'll react them with water. What I make on the other side is the conjugate acid and OH minus. Okay. So I know I can start to fill in my ice table. ICE. Now with the chemistry established, I know I have H2O liquid that I can cross out. I'm given 1.0 molar of NH3 to start with. There's no NH4 plus to start with. There's 1.0 times 10 to the minus 7th OH minus, but just like our acid examples, we're going to say that that's so small for this situation that we're going to call it 0. Our Q is equal to 0. Our Q is less than K. We're moving in the direction of the products again. We're moving in the unfavored direction, okay? So this is going to be a minus X here, 1.0 minus X. There's going to be a plus X here and a plus X here, X and X. We have a Kb. We have a set of E information. We can now solve for X. All right. Wait a second. We need to remember what X is. All right. X isn't going to be H plus information. X is going to be OH minus information. What we need is pH. So just make sure we kind of realize that, all right? We're going to solve for an X here, but we're going to need to do some extra work to get to pH info. So let's do the math. All right. Our Kb expression, then we can populate with that E information, Kb, which was given as 1.85 times 10 to the minus 5. It looks like OH minus and NH4 concentration at equilibrium in the numerator. So that's an X squared because each one of those was X. And then below that, we're going to do a 1.0. Did I do 1.00, 1.0? Let's do 1.00 minus X. Okay. We're moving it, excuse me. We're moving in the unfavored direction. So again, we're going to try the 5% rule. We also see that this is 10 to the 0, this is 10 to the minus 5. It fits like for a situation where we should use the 5% rule. So let's assume that X is way less than 1.00. Our math simplifies down. 1.85 times 10 to the minus 5 equals X squared divided by 1.00. Okay, so our X in this instance, all right, is going to be equal to 2.366414. Oh, sorry, my fault. Our X in this instance, my bad. Take the square root of both sides, and what you get is 0.00433012. I jumped ahead, right? This will have 3 significant figures. This is the concentration of OH minus at equilibrium. We're supposed to get a pH. So what I'm going to do next is I'm going to get a pOH. And I'm going to take the negative log of my OH minus concentration at equilibrium. When I take the negative log of this, my pOH that I get is 2.366414. Let's check significant figures. There's 3 significant figures here. So there would be 3 significant decimal places here. pH is always 14.00 minus pOH. Well, what did I just calculate? I just calculated pOH. And so when I do that subtraction, right, what I'm left with, let me just do a quick 14. What I'm left with is 11.63, limited to 2 decimal places because of this measured 14.00. My pH is 11.63. Now, does this make sense for a base? We knew we were using a KB, so we should end up with a pH that's greater than 7. And is that the case? Yes, that is the case. So just to review here, we set up our KB expression. We realize that our X doesn't give us H3O plus information directly. Our X gives us OH minus concentration, right? If the problem was calculate the pOH, you would stop here. But the problem asked for the pH. And so we have to remember how pOH and pH relate to each other. And our final answer is 11.63. So again, the math doesn't seem so difficult if you've practiced from the last set of videos. It's just some extra steps at the beginning to make sure you understand the chemistry, and then some extra steps at the end to make sure you can get to the information that you're supposed to get to. Expressing it in terms of pHs and pOHs is a common thing.